Welcome to G Fun Facts Online. Today, we are going to talk about a breakthrough that materials scientists have been chasing for 20 years. It is a story that combines quantum physics, accidental discoveries, and ancient Japanese sword-making techniques. We are talking about the creation of Goldene, the first ever freestanding, single-atom thick sheet of gold. To understand why this is such a monumental achievement, we have to go back to 2004. That was the year the world of materials science changed forever, with the isolation of graphene. Graphene is a single atomic layer of carbon. It sparked a literal gold rush for what we call two-dimensional materials. These are substances with a thickness measured in mere atoms. When you take a bulk material and strip it down to a single layer, it possesses exotic properties unseen in its three-dimensional counterpart. For 2 decades, scientists successfully flattened carbon, boron, silicon, and even complex oxides. But one material remained elusive. It stubbornly refused to enter the flatland. That material was gold. Known for its malleability and its tendency to clump into nanoparticles, gold was thought to be impossible to exfoliate into a freestanding single-atom sheet. But that changed in April 2024. Researchers at Link and Älping University in Sweden achieved the impossible. They created Goldene. This discovery is not just a triumph of synthesis, it is a gateway to a new era of metallines, promising to revolutionize catalysis, hydrogen production, and carbon capture. Today, we are going to tell the comprehensive story of Goldene. Let's start with the physics. To understand the magnitude of Goldene, one must first appreciate the dimensional frontier. We live in a three-dimensional world. For millennia, our materials, wood, stone, bronze, steel, have been three-dimensional. Their properties are defined by their bulk. Density, hardness, and conductivity are essentially averages of trillions of atoms interacting in a lattice. However, when you strip a material down to a single atomic layer, the rules of physics change. Electrons that were once free to move in 3 directions are confined to a 2-dimensional plane. This is called quantum confinement, and it fundamentally alters the material's behavior. Graphene, for instance, is not just thin graphite. It is a transparent, flexible superconductor of heat and electricity with a strength 200 times greater than steel. This phenomenon launched the hunt for other 2D materials. We found silicene, which is 2D silicon for electronics. We found phosphorine for optoelectronics, and boraphenine for mechanical strength. Yet, noble metals like gold, silver, and platinum posed a unique challenge. Why was 2D gold so hard to make? The answer lies in chemical bonding. Graphite consists of layers of carbon atoms. Inside a layer, the bonds are incredibly strong, but between the layers, the forces are weak. These are known as van der Waals forces. This allows you to slide the layers apart, like a deck of cards. This process is called exfoliation. You can essentially use sticky tape to peel graphene off graphite. Metals, however, do not work this way. In a bulk nugget of gold, the atoms are held together by metallic bonding. Electrons form a sea that flows freely around positive nuclei, creating a non-directional glue. There are no distinct layers to peel. If you try to thin gold out, the atoms, driven by high surface energy, will naturally clump together to minimize their exposed surface area. They form nanoparticles or islands, not sheets. For years, 2D gold existed only in sheets. Scientists would deposit gold atoms onto a substrate, like silicon carbide, that held them in place. While these were technically 1 atom thick, they were not freestanding. They were chemically married to their support, which altered their properties. The Holy Grail was a sheet of gold that could float alone. The discovery of Goldene was not the result of a direct pursuit, but a serendipitous accident, which is a hallmark of great scientific breakthroughs. The story begins at Link and Älping University with Lars Hultman, a professor of thin film physics, and Shun Kashiwaya, a researcher in the materials design division. The team was working with a class of materials known as max phases. These are layered, ternary carbides, or nitrides. They behave like a ceramic, hard and heat-resistant, but conduct electricity like a metal. Hultman's team was interested in titanium silicon carbide. They wanted to create a better electrical contact for this material, so they decided to coat it with gold. When they exposed the titanium silicon carbide to gold at high temperatures, they expected the gold to sit on top, forming a conductive layer. Instead, something bizarre happened. The gold atoms didn't just sit on the surface. They diffused into the material. More specifically, they kicked the silicon atoms out and took their place. The silicon evaporated away, and the gold atoms settled comfortably between the layers of titanium carbide. The result was a new material, titanium gold carbide. In this structure, the gold atoms were already arranged in single-atom thick planes, sandwiched between titanium carbide slabs. The team had inadvertently created a stack of Goldene sheets, but they were trapped inside a ceramic prison. This phenomenon is known as intercalation. It is similar to how lithium ions move into the graphite anode of a battery. But here, it was a total atomic substitution. The researchers realized they had a precursor material containing the prize. The challenge was now extraction. How do you remove the titanium carbide bread to leave only the gold ham? Usually, when scientists want to isolate a layer from a max phase, they use harsh acids like hydrofluoric acid to etch away the middle element. This creates MXenes, a popular class of 2D materials. But here the middle layer was gold. If they used standard etching techniques, they would dissolve the gold and be left with titanium carbide, the exact opposite of what they wanted. They needed a chemical that would eat the chemically robust titanium carbide, but leave the delicate gold monolayer untouched. This seemed chemically impossible. Lars Holtmann found the solution in the annals of history, specifically in the metallurgy of Japanese craftsmanship. For centuries, Japanese smiths have forged steel to create katanas and knives. A famous technique involves manipulating the carbon content of steel. To visualize the grain structure or aestheticize the blade, smiths used a specific chemical mixture to etch away carbon residues without damaging the high-quality steel. This mixture is called Murakami's reagent. It is a mix of potassium ferrocyanide, potassium hydroxide, and water. Holtmann and Kashiwaya hypothesized that this ancient reagent could be tuned to etch away the titanium carbide layers of their precursor while sparing the gold. The process, however, was not simple. Shun Kashiwaya spent years tweaking the parameters. If the reagent was too strong, it destroyed everything. If it was too weak, nothing happened. They found that a very low concentration was the Goldilocks zone. The etching process was also slow, requiring days to weeks of gentle reaction. But the most critical insight involved darkness. When Murakami's reagent is exposed to light, the ferrocyanide breaks down and releases free cyanide ions. Cyanide is famous in the mining industry because it dissolves gold. So if the lights were on, the reagent would dissolve the gold, destroying the Goldene. If the lights were off, the reagent would attack the titanium carbide but leave the gold intact. Kashiwaya had to perform the etching in complete darkness. Even after successfully etching away the titanium carbide, a physical problem remained. The gold sheets were released into the solution, but gold atoms are chemically sticky. Left alone, the sheets would curl up like dried leaves or clump together into a useless ball of gold nanoparticles. The solution was the addition of a surfactant, a soap-like molecule. The team used cysteine, a sulfur-containing amino acid. Sulfur has a high affinity for gold. The cysteine molecules attach themselves to the surface of the floating gold sheets, creating a protective buffer. Imagine the Goldene sheets as cornflakes floating in milk. Without the surfactant, the cornflakes get soggy and mashed together. With the cysteine surfactant, each cornflake is coated, keeping them separate and flat. This marked the birth of Goldene, freestanding, stable, single-atom thick gold. So what exactly is Goldene? It is a crystalline lattice of gold atoms arranged in a triangular, hexagonal pattern. Its thickness is a nominal single atom, approximately 0.4 nanometers. Interestingly, the lattice constant, the distance between atoms, is contracted by roughly 9% compared to bulk gold. This shrinkage is due to the loss of neighbors. Without atoms above and below to pull on them, the in-plane atoms pull tighter to each other. The most shocking property of Goldene is its electronic structure. Bulk gold is the quintessential metal. It conducts electricity perfectly because its electrons form a continuous band with no gaps. However, when you reduce a material to 2D, you limit the available energy states for electrons. Investigations suggest Goldene behaves like a semiconductor. X-ray photoelectron spectroscopy revealed that the binding energy of the gold electrons shifted by 0.88 electron volts compared to bulk gold. This shift indicates a change in the chemical environment and charge density. The gold atoms in Goldene are electronically different. They are essentially a new element. Possessing a band gap means Goldene could potentially be used to switch currents on and off, which is the basis of a transistor. This opens the door to gold-based electronics that are chemically inert, unlike silicon. Optically, bulk gold is yellow because of plasmonic resonance. Goldene, being only one atom thick, interacts with light differently. While currently produced as a colloidal suspension, which appears black or dark, theoretical models suggest its transparency, and interaction with specific wavelengths could be tunable. It could be used for transparent conductive films, potentially replacing indium tin oxide in touchscreens. The creation of Goldene is not just academic. It solves massive industrial problems. Gold is already one of the most important industrial catalysts, but it is expensive and inefficient. In a gold bar, 99.999% of the atoms are stuck inside the metal, doing nothing. Only the atoms on the surface can interact with chemicals. In Goldene, 100% of the atoms are on the surface. This means 1 gram of Goldene has the catalytic power of kilograms of bulk gold. This massive increase in efficiency could slash the cost of industrial gold catalysts. One of the most promising applications cited by the Link and OUM team is CO2 conversion. We need to capture carbon dioxide from the atmosphere and turn it into something useful, like fuel. Goldene atoms have dangling bonds, unsaturated valency. Because they don't have neighbors above or below, they are desperate to bond with passing molecules. This makes them hyperreactive. They can grab a CO2 molecule, destabilize the carbon-oxygen bond, and facilitate its conversion into hydrocarbons. Then there is hydrogen production. The green economy relies on hydrogen, which we currently produce via electrolysis. This requires catalysts like platinum or iridium, which are scarcer than gold. Goldene offers a tunable surface. By attaching specific molecules to the surfactant-stabilized goldene, the electronic properties can be fine-tuned to lower the energy barrier for splitting water. In the future, Goldene hydrogen could be a term for hydrogen produced via these ultra-efficient monolayer catalysts. Goldene could also act as a superfilter for water purification. With its superior surface area, it could catalyze the breakdown of organic pollutants or forever chemicals in water systems, utilizing light to drive the reaction. In medicine, gold is already biocompatible. Gold nanoparticles are used in photothermal therapy for cancer. Goldene could be far more effective. Its 2D nature might allow for better absorption of near-infrared laser wavelengths, which penetrate tissue. Furthermore, it could be cleared from the body differently than spherical nanoparticles, potentially reducing long-term toxicity concerns. The success with Goldene validates the Murakami etching method as a generalizable technique. The Link and OUM-LPing team has already hinted at applying this to other noble metals. We could see iridine or 2D iridium for heavy-duty industrial catalysis. We could see platinine or 2D platinum, which would be the holy grail for hydrogen fuel cells. We could even see silverine for unmatched antimicrobial properties. The max-phase precursor family is just one of hundreds of combinations. By swapping gold for platinum or palladium in the precursor, we could forge a whole periodic table of 2D metals. The immediate challenge now is stability. Goldene naturally wants to curl up, while surfactants keep it flat in solution. Integrating it into a dry device like a microchip is difficult. Future research will focus on van der Waals heterostructures, stacking Goldene between layers of graphene to encapsulate and protect it, and wafer-scale synthesis to move from flakes in a beaker to mass production. For thousands of years, gold was the symbol of immutability, the metal that never changes, never rusts, and stays forever golden. Goldene proves that even the most stubborn elements can be transformed if we change their perspective. By forcing gold into 2 dimensions, we have stripped it of its nobility and given it a job. It is no longer just a shiny metal. It is a semiconductor, a catalyst, and a chemical worker. The discovery of Goldene in 2024 is likely to be remembered as a pivotal moment in materials science, comparable to the isolation of graphene. It reminds us that the periodic table is not a static list of ingredients, but a set of possibilities waiting to be unlocked by the geometry of the atomic world. We have entered the golden age of the flatland. Thanks for listening to G Fun Facts Online.